Where did water come from? 4.5 billion years ago, Earth was off to a rocky start. We'd just collided with another early planet the size of Mars, a cataclysmic event that melted both planets and spun off a sizable chunk of lava that cooled into our moon. This impact set the stage for the hadean eon, named after Hades, the Greek god of the underworld. It was a name that matched Earth's generally hellish vibes at that point, since our planet was so hot that our atmosphere actually contained vaporized gaseous rock. It was around 2000 degrees Celsius. But as the Earth and the Moon began to cool, something new formed on Earth's surface: liquid water. 71% of the Earth is covered in our estimated 366 trillion gallons of water. Except, we shouldn't have that water. We formed too close to the Sun. Mercury, Venus, and Mars are all super low on water, so where did ours come from and why do we have so much of it? Well, it's complicated and still debated, but we think our water came from a few unlikely sources such as meteorites, space dust, and even the Sun. Water itself isn't actually that uncommon in our solar system, it's just further out. In the beginning of our solar system, we all star stuff. Our solar system is formed from a nebula, the dusty remains of an exploded star. As that stardust collided and collapsed, it formed our Sun. And the gravity of that young Sun made all the rest of the dust spin around it in a flat plate-like cloud called the protoplanetary disk. But our early Sun was hot, and soon that disk of dust began to differentiate. Solar and magnetic winds blasted light gases away from the Sun, leaving mostly heavier elements like iron and silica behind. Which is why Earth is a rocky planet. That's what was in our section of the disk: lots of iron and lots of silica. We also had some of the ingredients for water. Water is made of hydrogen and oxygen is pretty heavy, so we have a lot of it. In fact, though it makes up only about 21% of our atmosphere, oxygen binds so readily to silica and iron that it's the most common element on our planet. But oxygen is only part of what you need for water, and hydrogen is really light, so it got blown out towards Jupiter, Saturn, and other planets, which now have a lot of water ice. So if it didn't form here to start with, where did we get that missing ingredient? Where did our hydrogen come from, and when did it get here? The easy answer is, we got pelted with it. Water ice and hydrogen hang out in the outer solar system, but sometimes they come inwards in the form of space pebbles like asteroids and meteorites. And there is a specific type of meteorite called a chondrite that is full of water. Instead, the solo hydrogen and the complete H2O water molecules have become part of the chemical structure of the minerals that make up chondrites. These include minerals like serpentine, chlorite and smectite, which hold on to their water tight. This is actually how most of Earth's water is stored today. We estimate that Earth's rocks hold maybe 18 times the amount of water that our oceans have. So how do you get that water out of these minerals? Well, the easiest way is to melt it. Which isn't always going to happen just by flinging those water-bearing minerals at the Earth. After all, we have solid chondrite meteorites that hit our planet and didn't melt. But that's because they hit today. Back in the beginning of the hadean, anything that hit the surface would have just melted straight into our magma oceans. There, hydrogen met oxygen and the resulting water superheated into gas. Lighter than magma, the water vapor would bubble up and out into our atmosphere. But this process was a race against the clock, because our magma surface was cooling, and once a solid lid of rock formed, no more water could escape. The oldest traces of rocks we've found date to about 4.4 billion years old, so that's probably when the lid of solid rock formed. But those rocks have signs of something surprising: they were exposed to a liquid ocean. As soon as the Earth cooled enough to put a cap on the magma, we had an ocean. Earth's atmosphere in the early hadean was full of carbon dioxide and was very thick, potentially as thick as 215 bars of pressure, which is 215 times what it is now. Today, water turns to gas when it reaches 100 degrees Celsius. But if you change the pressure, you can change when water turns to gas. By the end of the Hadean, 4 billion years ago, the surface of the Earth was very similar to what it's like today, a rocky crust, an ocean of liquid, but not superheated, water and an atmosphere of about the same pressure as today. So from meteorites to magma to air to superheated oceans, that should be the story of Earth's water. Turns out, the chemical composition of the water and hydrogen in chondrite meteorites doesn't actually match the chemical composition of most of the water on Earth. When we say chemical composition, what we mean is isotopes, or types of hydrogen. There are two really important isotopes of hydrogen, the regular brand, with 1 proton and 1 electron, and what's known as deuterium, with a proton and neutron. The addition of a neutron makes deuterium heavier than regular hydrogen. Most of the deuterium in our solar system was actually formed in the Big Bang. And it's a huge component of chondrite meteorites. They're heavy with this old type of hydrogen. The oceans are pretty heavy too, but our modern oceans aren't actually a great representation of our early water. For one, they're not 230 degrees Celsius, and for another, they've been sitting on our surface for 4.4 billion years. When Earth's magma oceans cooled enough to form a seal of hard rock, not all the water in the magma escaped into the atmosphere. A lot of it was trapped below the surface in a layer of Earth known as the mantle. Over time, pieces of the mantle have been shoved to the surface through plate tectonics, and we've been able to look at the hydrogen the rocks of the mantle contain. And it's a lot lighter than the hydrogen we see in the oceans. Which is part of why the source of Earth's water is still somewhat debated. In 2021, scientists reported on some interesting samples that were collected from an asteroid and maybe came up with the answer. They found that the samples had a uniquely high level of light hydrogen. But to confirm their growing suspicions of where that hydrogen came from, they had to replicate the process. So they measured the hydrogen and water content of olivine crystals before and after they exposed them to the equivalent of solar wind. When they looked at them afterwards, they found that, just like the asteroid samples, they had a crust of accumulated water built with light hydrogen. So where did this light water come from? Well, it's literally light water because it came from the sun. Solar winds from our sun shoot out a lot of particles, including protons. When those protons hit dust in their path, they can sometimes steal an electron. And a proton plus an electron is light hydrogen. Slam that light hydrogen into a rock with some oxygen in it and boom, you've made light water.